Night has fallen on the solar system. Closest to the Sun, the inner planets glow in tight, bright orbits. Farther out, Jupiter and Saturn move with slow authority. Beyond Neptune, the Kuiper belt stretches like a faint, icy ring. And then, if you follow the orbits out past where the diagrams usually stop, there is darkness. Not empty, but filled with something we can't see directly, a vast, almost invisible ocean of comets. That ocean is the Oort Cloud. It does not appear in photographs. No spacecraft has ever crossed it. Yet every time a long-period comet suddenly appears in our skies, it feels as if one droplet from that distant sea has finally fallen inward, reminding us that the solar system is much larger and much stranger than the map on a textbook page. This episode is a guided journey into that unseen frontier, what the Oort Cloud is, how we think it formed, and why every bright, long-period comet may be a one-time visitor from the farthest edge of our sun's domain. What the Oort Cloud is an invisible, spherical reservoir. If you picture the Kuiper belt as a wide, flattened ring of small bodies beyond Neptune, the Oort Cloud is something very different. Instead of a ring, imagine a shell. The Oort Cloud is thought to be a roughly spherical swarm of icy bodies surrounding the Sun in all directions, like a fragile halo. Its inner regions probably begin at distances of a few thousand astronomical units, AU, from the Sun, thousands of times farther than Earth, and may extend to tens of thousands of AU, perhaps up to a distance where the Sun's gravity is only barely stronger than the collective pull of the galaxy. The objects in this shell are small, frozen planetesimals a few kilometers across, maybe smaller, made of water ice, carbon dioxide, carbon monoxide, methane, ammonia, mixed with dust and rock. They are the same basic ingredients we see in comets and icy bodies closer in, but stored under extreme cold and deep darkness for billions of years. We have never imaged an Oort Cloud object directly. They are simply too distant and faint. So why do we believe this cloud exists at all? The main clues come from the orbits of long-period comets. Some comets have short periods, a few years to a few decades. They return again and again, and their orbits lie roughly in the same plane as the planets, consistent with an origin in the Kuiper belt or scattered disk. But others are different. Long-period comets can have orbital periods of hundreds of thousands or even millions of years. Many of them arrive on extremely elongated orbits that are only barely bound to the Sun, approaching from directions that are almost random in the sky. Their paths are not concentrated in the plane of the solar system. Instead, they come from every angle. If you work backward from those orbits, the simplest explanation is that these comets start in a distant, nearly spherical distribution of icy bodies surrounding the Sun, a reservoir so large and diffuse that an occasional tiny gravitational nudge can send one object sliding inward, turning an almost invisible member of the cloud into a sudden, bright comet in our skies. In other words, we infer the existence of the Oort Cloud from the raindrops, the long-period comets, that occasionally fall from it. How the Oort Cloud formed, scattering and gentle capture. To understand how such a distant structure could exist, we have to rewind the clock to the earliest era of the solar system, when the planets were still forming. Billions of years ago, the region beyond the young giant planets was not empty. It held a massive disk of icy planetesimals, small bodies formed from the same disk of gas and dust that produced Jupiter, Saturn, Uranus, and Neptune. These planetesimals orbited the young Sun in relatively flat, disk-like orbits, just as the planets did. The giant planets, still settling into their own orbits, scattered these smaller bodies gravitationally. Every close encounter between a massive planet and a small icy body acts like a gravitational slingshot. Some planetesimals were deflected inward, where later encounters with Jupiter or Saturn sent them on paths that intersected the inner solar system. Others were flung outward, their orbits stretched until they reached thousands of AU from the Sun. On their own, those outward scattered bodies would still be on elongated, bound orbits that pass back through the planetary region. But over millions of years, additional effects come into play. Passing stars, drifting tens of thousands of AU away, exert slow, cumulative tugs on these distant orbits. The large-scale gravitational field of the Milky Way, known as the galactic tide, also acts gently on objects that are barely bound to the Sun. Together, these distant perturbations can transform an elongated, planet-crossing orbit into a more distant, nearly circular one, lifting its closest approach away from the realm of the planets. Over time, many scattered planetesimals are puffed up into a spherical distribution, their orbits randomized in orientation, their perihelia raised, their semi-major axes stretched to tens of thousands of AU. The result is what we call the Oort Cloud. The relic population of icy bodies that began life in the planetary disk were scattered outward by the giant planets, and then gently reshaped by the galaxy into a vast, almost isotropic shell. In the outermost regions, sometimes called the outer Oort Cloud, the sun's grip is especially weak. There, even a modest perturbation from a passing star, or the slow stretch of the galactic tide, can slightly tilt or shrink an orbit so that the object's perihelion drops back down into the inner solar system. When that happens, a body that has spent billions of years in deep freeze begins its long fall toward the sun and becomes, from our perspective, a new long-period comet. Long-period comets, one-time visitors from the invisible ocean. From the ground, a bright long-period comet appears suddenly. For most of its existence, it is essentially invisible, a dark nucleus less than 20 kilometers across, orbiting tens of thousands of AU from the sun. Then, some subtle gravitational push, perhaps from a distant star that passed by millions of years ago, changes its orbit, sending it inexorably inward. At first, nothing appears different. For thousands of years the comet is still so far away that the sun is just another bright star. But gradually, as it approaches the inner few AU, sunlight begins to matter. The nucleus warms. Ices near the surface start to sublimate. Gas expands outward, dragging dust grains with it. A tenuous atmosphere, the coma, forms around the nucleus, and the solar wind begins to shape two tails, a pale, curved dust tail, and a straighter plasma tail pointing away from the sun. By the time the comet is visible in Earth's skies, most observers will just see a beautiful, glowing object. But dynamically, what we are witnessing is a rare event, a single, small member of the Oort Cloud making possibly its first and only passage through the inner solar system. Many long-period comets follow orbits that are close to parabolic. Some are bound, with periods measured in hundreds of thousands or millions of years. Others may gain enough energy during planetary encounters to escape entirely, leaving the solar system forever. For a given comet, we might only ever see one apparition. That is why each long-period comet is so scientifically valuable. It is a one-time sample from a part of the solar system we cannot yet visit. Its ices retain information about the temperature and composition of the region where it formed. Its orbit encodes the gentle tugs of passing stars and galactic tides over billions of years. We classify some of these as dynamically new comets, objects whose orbits suggest that this is their first entry into the inner solar system. In those cases, the surface may be particularly pristine, with ices that have barely been processed by previous passages near the sun studying their spectra, activity, and dust gives us a glimpse of the Oort Cloud's raw material as it truly is, not as it becomes after thousands of cycles of heating and cooling. In that sense, every long-period comet bright enough to study in detail functions like a probe launched from the Oort Cloud long before humans existed, now finally arriving where our telescopes can read its message. Living inside an invisible ocean. When we look at diagrams of the solar system, they often stop just past Neptune, with a thin line marking the Kuiper belt and a blank beyond. The reality is more humbling. Our sun is not surrounded by emptiness. It is wrapped in a vast, diffuse halo of ancient ice and rock, trillions of small bodies moving slowly in the dark, tracing elongated paths that may take millions of years to complete a single orbit. From our vantage point on Earth, inside the tiny inner cavity of this structure, the Oort Cloud is effectively invisible. Its objects are too cold and faint to detect individually with current instruments. We know it is there only because, every so often, one of its fragments is tipped inward, lights up as a comet, and then either returns to the dark or leaves forever. That means we live deep inside a silent, frozen ocean without ever seeing its surface. For now, the Oort Cloud is a theoretical landscape, built from the orbits of long-period comets, from models of planet formation and galactic tides, from indirect evidence rather than direct photographs. But its consequences are real. It is the source of many of the most spectacular comets in human history, and a fossil structure that preserves the early scattering history of the giant planets. One day, far in the future, human technology may reach the point where we can send probes into that distant halo, or build telescopes capable of directly detecting its largest members. Until then, every bright long-period comet is a brief window into that realm, a reminder that our planetary system is embedded in a much larger structure that we have only just begun to imagine. We often say we live in the solar system. More accurately, we live near the center of an immense, nearly invisible shell of ancient comets, an Oort Cloud that quietly encases our world, holding in its darkness the oldest ice the Sun ever made. What is the Oort Cloud? Our second, spherical architecture. Far beyond Neptune and the Kuiper belt, the familiar architecture of the solar system fades into darkness. If you could keep flying outward, past the orbits of the giant planets and the thin disk of Kuiper belt objects, you would eventually enter a region with no obvious landmarks, just starlight, cosmic night, and an almost invisible population of frozen worlds. That vast, hidden frontier is what we call the Oort Cloud. It isn't a neat ring like the asteroid belt, and it isn't a flat disk like the Kuiper belt. It is more like a three-dimensional shell of icy bodies surrounding the Sun from all directions, a ghostly sphere of comets that marks the true outer edge of our planetary system. Astronomers usually divide this distant reservoir into two broad regions. The inner Oort Cloud, sometimes called the Hills Cloud, likely begins at distances of a few thousand astronomical units. 1 astronomical unit, or AU, is the distance from Earth to the Sun. By the time you reach a few thousand AU, you are already tens of times farther out than Pluto. Out there, the Sun's gravity still dominates, but only loosely. Objects move slowly, on orbits that take millions of years to complete. Beyond that lies the outer Oort Cloud, which may extend to tens of thousands, perhaps up to around 100,000 AU from the Sun, roughly halfway to the nearest stars. At those distances, the Sun's grip is barely stronger than the gentle tidal pull of the Milky Way itself. Passing stars, giant molecular clouds, and the overall galactic tide can all tug on these distant bodies, gradually reshaping their orbits over billions of years. Within this enormous volume, models suggest there may be hundreds of billions to maybe trillions of icy objects. Most are probably only a few kilometers across, some may be tens of kilometers. In composition, they are thought to resemble the long-period comets we occasionally see in the inner solar system, mixtures of water ice and other frozen volatiles like carbon monoxide, carbon dioxide, methane, and ammonia, all laced with dust and complex organic material. Each one is effectively a small, frozen nucleus of cometary ice, stored at temperatures only a few degrees above absolute zero. The paradox of the Oort Cloud is that we cannot see it directly. No telescope has yet imaged an individual Oort Cloud object in its distant home. They are simply too small, too dark, and too far away to reflect enough sunlight for us to detect. Instead, we infer the cloud's existence from the behavior of the comets that occasionally fall inward toward the Sun. When a comet appears on a very long, highly elongated orbit, with a period of hundreds of thousands or even millions of years, and when its trajectory seems to come from a random direction in the sky rather than from the plane of the planets, that is a powerful clue. The pattern we see is that these long-period comets arrive from nearly all directions, forming an almost isotropic distribution on the sky. If their source were a flat disk like the Kuiper belt, we would expect them to arrive mostly near the plane of the solar system. Instead, their approach directions look like points sprinkled over a sphere. The simplest explanation, and the one that has held up for decades of observations, is that the Sun is surrounded by a roughly spherical swarm of distant icy bodies, and that from time to time, one of them is nudged inward by a passing star or by the slow tidal pull of the galaxy. When that happens, its orbit shrinks from a distant, almost circular path in the far cloud to a long, stretched ellipse that carries it into the inner solar system for the first time. We see that brief visit as a bright, long-period comet. So while the Oort Cloud has never been photographed as a whole, its signature is written in the orbits of the comets that appear from nowhere and then vanish back into the dark. Together, those trajectories trace the outline of a structure we cannot yet see, a vast, spherical comet ocean that marks the true, diffuse border of the Sun's domain. In the beginning, the solar system was not a tidy family of planets and belts. It was a crowded construction site. Around the young Sun, a thick disk of gas and dust rotated like a slowly turning storm. Within that disk, tiny dust grains stuck together, forming pebbles, then boulders, then kilometer-scale bodies, planetesimals. Closer in, these early building blocks were mostly rocky. Farther out, beyond the snow line where water and other volatiles could freeze, they became mixtures of rock and ice, the seeds of comets and icy worlds. In this outer region, the giant planets were assembling. Jupiter, Saturn, Uranus, and Neptune did not simply appear in their present orbits. They grew by sweeping up gas and solids, and their gravity began to dominate their surroundings. Each time an icy planetesimal passed too close, it felt a powerful slingshot. Some of those close encounters were gentle, nudging the object into a slightly different orbit. Others were catastrophic for the orbit, though not for the body itself. A single pass near Jupiter or Saturn could transform a modest, nearly circular path into a long, stretched ellipse that carried the planetesimal far from the Sun. In many cases, repeated encounters pumped up the orbital energy until the object was ejected completely, set loose into interstellar space. But not all of these scattered bodies escaped. A large fraction ended up in a kind of limbo, orbits so vast and elongated that they carried the object tens of thousands of astronomical units from the Sun, yet still technically bound to it. At that distance, the Sun is no longer a blazing disk in the sky. It is just another bright star among many. The gravitational grip is very weak, and that weakness is the key to building the Oort Cloud. In the first few 100 million years of solar system history, the Sun did not travel alone. It was born in a cluster of other stars, moving together through the galaxy. Some sibling stars passed relatively nearby on astronomical scales, perhaps within a light year or so. Later, as the Sun drifted out of its birth cluster and into the wider disk of the Milky Way, it began to feel the large-scale gravitational tide of our galaxy, a steady, gentle pull that acts differently on objects at different distances. These external forces matter most for the bodies on the widest, loosest orbits, precisely the ones that had been scattered outward by the giant planets. When such an object swings out to its farthest point from the Sun, it is moving very slowly. A weak tug from a passing star or from the galactic tide can, over many millions of years, significantly change the shape and orientation of its orbit. Bit by bit, those elongated ellipses are twisted and rounded. Instead of diving back through the plane of the planets, some of these orbits are tilted, rotated, and puffed up into a more spherical distribution. Perihelia, the closest points to the Sun, can be lifted out of the planetary region, so that these bodies no longer cross the paths of Jupiter or Neptune at all. Once that happens, the giant planets can no longer efficiently scatter them. They are effectively parked in a distant halo. Over time, countless individual stories like this, one icy body after another being scattered outward by a planet and reshaped by the galaxy, add up to a structure, the Oort Cloud. Closest in, at perhaps a few thousand astronomical units, lies what many models call the inner Oort Cloud or Hill's Cloud. Here, objects are still loosely bound, but the Sun's gravity has a firmer hold. Their orbits are large and often inclined, yet not so fragile that a single stellar passage will easily knock them free. Farther out, into tens of thousands of astronomical units and possibly approaching ~100,000 AU, roughly 1 to 2 light-years, the outer Oort Cloud becomes a realm where the Sun's gravity is barely stronger than the background gravitational field of the galaxy. Bodies there are bound, but only just. A modest nudge from a star gliding past in the distant DAC can be enough to change their trajectories dramatically. Not every scattered planetesimal finds a long-term home. Many are thrown completely out of the solar system during the scattering phase, especially those that have very close encounters with Jupiter. Others remain in intermediate orbits, gradually destabilized and lost over billions of years. The Oort Cloud is, in this sense, the surviving remnant of a far larger population. Estimates suggest it may contain hundreds of billions to trillions of icy bodies, but the exact number remains uncertain. We infer its existence and rough scale not by seeing it directly, but by watching what occasionally falls inward from it. When one of these distant objects has its orbit slightly modified, by a passing star, or by the galactic tide acting over long timescales, its perihelion can be lowered back into the planetary region. The once distant body then becomes a long-period comet, on a highly elongated orbit that can take it from the inner solar system back out to tens of thousands of astronomical units. The nearly random directions from which these comets arrive, spread over the entire sky, are one of the strongest fingerprints of a roughly spherical reservoir enveloping the Sun. Crucially, the Oort Cloud is not a new structure being actively built today at any significant rate. The heavy scattering that populated it was most intense during the early, chaotic era, when giant planets were still migrating and the leftover planetesimal population was dense. Today, the process continues at a much slower pace. A few additional bodies may still be scattered outward, and some may be lost to interstellar space, but the basic architecture of the cloud is a fossil from a much younger solar system. In that sense, the Oort Cloud is a memory. It is the echo of a time when the forming planets rearranged vast numbers of icy building blocks, flinging many away and leaving a diffuse halo behind. We live deep inside that halo, near its warm center, mostly unaware of the silent ocean of comets that surrounds us because it is almost entirely invisible. To visualize its formation, imagine following a single icy planetesimal born near the young Neptune. It orbits quietly for a time, until a close encounter with the growing planet launches it onto a long, stretched path. It races away from the sun, slows, and then falls back inward, only to be scattered again. After several such encounters, it finds itself on an orbit that reaches far beyond the planets. At its most distant point, a passing star slightly twists the orbit, tilting it out of the planetary plane. Over many revolutions, gentle tugs from the galaxy smooth and randomize its path. Eventually, it no longer comes anywhere near the planets. It simply drifts, cold and dark, on a vast loop around the sun, one faint, frozen particle in the Oort Cloud. When we look up and see a bright comet hanging over the horizon, it feels sudden, as if it has appeared out of nowhere. Dynamically, that is almost true. Many of the most spectacular comets we've ever seen began their journey in a place so distant, so dark, that not even our largest telescopes can pick them out individually. The Oort Cloud. Long-period comets are the rare moments when that invisible halo becomes visible. Astronomers divide comets into two broad dynamical families. Short-period comets complete an orbit in a human timescale, years to a couple of centuries. Their paths are modestly elongated and typically stay close to the plane of the planets. Many of them can be traced back to the Kuiper belt and the scattered disk, flattened reservoirs of icy bodies beyond Neptune that we can now map and model. Long-period comets are different. Their orbits can take thousands, hundreds of thousands, or even millions of years to complete a single loop around the sun. Instead of moving roughly in the planetary plane, they approach from almost any direction in the sky. Some plunge inward on orbits so stretched that, mathematically, they are barely bound to the solar system at all. Their paths are close to perfect parabolas. When we plot the incoming directions of these comets on the sky, the pattern is striking. They come in nearly isotropically, from all over the celestial sphere, not from a flattened disk. That simple fact is one of the key clues that something like the Oort Cloud must exist, a spherical, distant reservoir surrounding the solar system in all directions. Most of the time, the trillions of icy bodies in that halo do nothing dramatic. They orbit slowly, far beyond the planets, locked in a gravitational compromise between the pull of the sun and the very gentle tug of the galaxy and passing stars. Over millions and billions of years, though, tiny changes in their orbits add up. A nearby star passes within a few light years and nudges a group of objects by a fraction of a meter per second. The tidal field of the Milky Way slightly warps their elongated paths. Occasionally a giant molecular cloud or other large mass in our galactic neighborhood adds its own subtle pull. For any one of those bodies, the change is small, but if its orbit is already very wide and loosely bound, even a small perturbation can push the perihelion, the closest point to the sun, down into the region of the planets. The object that has spent billions of years in deep freeze suddenly finds itself on a long, slow dive toward the inner solar system, falling sunward for the very first time. These first-time visitors are often called dynamically new comets. Because they have never before come close to the sun, their surfaces can still preserve highly volatile ices just below the outermost layer, carbon monoxide, carbon dioxide, and other species that are easily lost in repeated heating cycles. As they approach the inner solar system, sunlight wakes those ices in dramatic fashion. Jets erupt from the nucleus as trapped gases escape through fractures and vents. A diffuse coma of gas and dust swells around the nucleus, and solar radiation pressure stretches dust into a broad, curved tail while the solar wind pulls ionized gas into a straight, blue-white streamer. By the time such a comet becomes visible to the naked eye, most of its nucleus is still just a few kilometers across, a small, black, irregular chunk of ice and rock. The huge structure we see is almost all atmosphere, a temporary envelope that can be tens of thousands of kilometers wide. To an astronomer, that coma is a gift. Spectrometers can break its light into colors and read the fingerprints of volatile molecules, water, carbon monoxide, carbon dioxide, simple and sometimes more complex organics. In that spectrum is a record of the temperature and chemistry in the region where the comet once formed, billions of years ago. Comets like Hale-Bopp in the 1990s, with its immense, long-lived tail, are spectacular examples of what an Oort Cloud visitor can look like. For months, it dominated the sky, but dynamically it was just one icy grain dislodged from a colossal, unseen reservoir. Its orbit was so elongated that, after its brief visit, it headed back outward on a path that will not bring it close again for thousands of years. Many long-period comets will never return at all. Some are perturbed onto slightly hyperbolic orbits and escape into interstellar space after a single pass. From a scientific perspective, each long-period comet is a one-shot probe delivered from the far edge of the solar system. We do not control when they arrive or which one we get. The galaxy does the scheduling. But every time one arcs in from a random direction, lights up near the sun, and then vanishes again into the dark, it briefly turns the hidden Oort cloud into something we can measure, analyze, and learn from. In that moment, a structure we can't see directly, a distant sphere of ancient ice, announces its presence in the form of a bright, transient visitor. Long-period comets are the messengers. The Oort cloud is the silent ocean they come from. Far above the blue curve of Earth, past the thin halo of our atmosphere and the quiet orbit of the Moon, the solar system looks tidy. 8 planets, a few belts of small bodies, all circling a single star in a flat, elegant plane. It's the version we see in textbooks, a family portrait cropped tight around the familiar. Now imagine pulling the camera back. We glide beyond Mars and the rubble of the asteroid belt, past Jupiter's storms and Saturn's rings, past the distant ice giants Uranus and Neptune. The last bright planet shrinks to a pale dot. Beyond it lies the Kuiper belt, a wide, faint ring of frozen worlds. To many diagrams, that is where the solar system ends. But we keep going. As the sun dims to a bright star behind us, another structure emerges in our imagination, a vast, nearly invisible cloud of ice and dust that surrounds everything we've just flown through. It is not a disk, not a ring, but a sphere, a ghostly shell of comets stretching out in every direction, so large that light itself needs months to cross even a small fraction of it. This is the Oort cloud, the invisible ocean around the sun. We cannot see it directly. Its individual inhabitants are small and dark, frozen to just a few tens of degrees above absolute zero. They drift slowly on enormous orbits, thousands to tens of thousands of times farther from the sun than Earth is. From each icy body, the sun is not a warm, golden disk, but a distant point of light in a black sky. And yet we know this ocean is there because, from time to time, one of its drops falls inward. We notice them as long-period comets, newcomers that appear from seemingly random directions in the sky, on orbits so stretched that they may take millions of years to complete a single loop around the sun. Many of them are probably visiting the inner solar system for the first time since they formed, back when the planets were still assembling. Their paths, when traced backward with celestial mechanics, point not to the flat Kuiper belt, but to a distant, spherical reservoir. The almost uniform spread of their arrival directions across the sky is the fingerprint of that halo. The story of the Oort cloud begins in the crowded, chaotic youth of the solar system. As the giant planets grew, they acted like gravitational slingshots, flinging countless icy planetesimals outward. Some escaped entirely, lost to interstellar space. Others did not quite get away. They climbed far out on elongated orbits and then, over millions of years, were gently reshaped by the tidal pull of the Milky Way and the passing of nearby stars. Those tugs rounded their paths and tilted them into every conceivable orientation, inflating a loose swarm into a spherical shell. Today, that shell is a fossil of that early chaos. It remembers how strongly the giant planets scattered material, how many icy worlds were built and then exiled to the dark. Its inhabitants are time capsules, preserving cold ices and dust from an era long before Earth's surface cooled enough for oceans. From our perspective on the inner worlds, the Oort cloud is almost entirely theoretical, a structure inferred from the motions of the comets that occasionally grace our skies. But those rare visitors carry a quiet message. Their ices and dust grains still hold the chemistry of their birthplace. Their elongated orbits trace the shape of the distant reservoir they came from. Each one is a tiny, natural probe from a region we have never reached with spacecraft and likely will not touch directly for many human lifetimes. We live under blue skies and think of the solar system as a disk of planets, moons, and belts. In reality, we live deep inside a gigantic, nearly invisible ocean of comets. Far beyond Neptune, in a darkness we have never seen with our own eyes, countless icy bodies drift in slow, patient orbits around our star. Every so often, one of those bodies is nudged just enough to fall inward. It travels for millions of years through the cold, and then, in a matter of weeks, writes a bright, brief line across Earth's night sky before fading again into the dark. Each one is a reminder that our map of the solar system is still incomplete, and that around the small, warm world we call home, an ancient frozen ocean silently waits.